Hello and welcome to The Space Above Us. Episode 68, Space Shuttle Flight 1, STS-1, the greatest test flight. Last time, we took one last quick tour around the shuttle program before declaring ourselves ready for launch. The original plan was to start flying sometime in 1979, but that had to be pushed back by nearly 2 years. As always with a complex program like this, you can't really point to any one specific thing and say, yes, this is where the problem was. But as we learned, there were definitely some aspects that contributed more than others. But I suppose that with a project as massive as the shuttle, some delays were to be expected. And the astronauts were happy to have a little extra time to iron out procedures and squeeze in some more training. In any case, the important thing was that at long last, the space shuttle was ready to fly. The mission we'll be discussing today is STS-1, short for Space Transportation System 1. Its primary objective? To demonstrate the safe launch into orbit, re-entry, and landing of the space shuttle. Though it would also be examining the performance of the spacecraft and its various subsystems. The vehicle for this mission was OV-102, which had been dubbed Columbia. Each element had been tested in isolation, but STS-1 would be the first time that all of the components of the space shuttle were brought together and actually flown. The first flight of any new vehicle is always noteworthy, but STS-1 really stands out for one reason in particular. Columbia would fly with a crew on board. The space shuttle was the first, and at the time of this recording, only time that a piloted orbital spacecraft was flown by a crew on its first flight. At first glance, this seems a little crazy. Project Mercury, Project Gemini, and the Apollo program all flew with uncrewed capsules as part of their test flights. So why take the risk with the shuttle? There were a number of reasons, so let's look at a few. First, despite the thousands of hours spent in simulation testing, including state-of-the-art hypersonic wind tunnels, a lot remained unknown about the hypersonic flight regime. The orbiter was a winged spacecraft and would be entering the atmosphere at over 25 times the speed of sound. And there just wasn't a ton known about how things behave at those speeds. They knew enough that the engineers were confident that the orbiter would be able to survive, but there was enough wiggle room that automating the entry would be really tricky. They tuned the autopilot such that it had more room to play than later flights would, allowing it to deviate further from the expected entry control inputs. But what NASA really needed was a system that could adapt to developing conditions on the fly. A system that could make decisions outside of the rigid bits and bytes of a normal computer. A system that could draw on decades of experience and intuition to guide the shuttle home. And that system had a name. Astronauts. Another important reason is that the astronauts themselves lobbied hard for this. I think when you hear that the first test flight of a vehicle had people on board, you can conjure up this image of the crew dutifully resigning themselves to what amounted to a suicide mission. But nothing could be further from the truth. The 2 seats on the first shuttle flight were highly sought after. They would be the lucky duo to be the first to truly explore the orbiter's flight envelope, to draw upon their impressive skills to usher home a multi-billion-dollar spacecraft. That's a test pilot's dream. They also had a strong interest in making sure that the orbiter couldn't be too automated. If an uncrewed shuttle could fly and land on its own as a test flight, then they believed it wouldn't take long for an operational flight to launch without a crew. With the robotic arm in the payload bay, it was possible that an entire operational flight could be commanded from the ground. The astronauts didn't like the precedent and wanted to make sure that a crew was on board from day one. It's also worth noting that this decision shed some light on how NASA thought about the shuttle. No one bats an eye at a pilot being on board for the first flight of a fighter jet, or something like a 747, or even the X-15. I think by flying with a crew from the start, NASA, intentionally or not, was framing the shuttle less as a limited experimental run and more as something routine. So STS-1 would have a crew. But what was the plan if something went wrong? When strapping yourself to a few million pounds of explosives, it's always a good idea to have a backup plan. In Project Mercury and the Apollo program, the crew capsule would be dragged away from a failing rocket by a launch escape system powered by a small-ish solid rocket. One of the benefits of putting your crew on top of a rocket is there's nothing in the way if you need to make a quick escape. But while the crew sat at the top of the orbiter itself was an enormous spacecraft attached to the side of the main launch vehicle. A traditional launch escape system was not going to work. Crew escape is a topic that we will sadly have cause to revisit in detail in the future, but let's quickly go over the options. The first 4 flights were known as the orbital test flights, and in a nod to the uncertainties that came with these test flights, Columbia was equipped with 2 high-altitude ejection seats. If required, the crew could activate these seats, the ceiling panels, including switches and controls, would be instantly jettisoned through some engineering miracle that I don't understand, and the commander and pilot would be rocketed out through the ceiling of the crew cabin. From there, they would be kept safe by spacesuit-like pressure suits until they deployed their parachutes and were recovered. If this sounds familiar, it's because that's exactly what the plan was on Project Gemini. On both vehicles, these ejection seats could only be used for the first few minutes of flight. After that, they were too high and too fast. But it wasn't quite that simple. Any contingency that required crew escape was constrained by 2 big white fire-breathing problems: the solid rocket boosters. As discussed previously, SRBs, once lit, cannot be deactivated. They burn until they stop, and the only way to change that is for the range safety officer to blow them up. So if something went wrong during the first 2 minutes or so of the flight, there wasn't much the crew could do but wait it out. Theoretically, they could jettison the SRBs. There was a manual switch in the cockpit, but that would likely tear apart the vehicle. They could also theoretically eject during this phase, but since the SRB plumes grew with altitude, no one was really sure how launching an ejection seat through them would work out. But I'm going to go out on a limb here and say that it wouldn't be great. This raises the obvious question: what if something goes wrong with the SRBs? Well, again, we'll obviously have cause to get deeper into this one a little bit down the road, but the short answer is that nobody expected that. Compared to the rest of the vehicle, the SRBs were super simple, super tough, and super reliable. Chris Kraft even said that the SRBs were the escape system. They would reliably get the orbiter away from the launch site and buy time for the crew to figure out what to do in the far more likely scenario of a space shuttle main engine failure. So, we wait out the SRBs. Depending on the nature and timing of the problem, there are a few options for what to do after SRB SEP. The most desirable option is an abort to orbit, which allows you to limp into orbit even if it's not the one you were planning on. Then you can take your time diagnosing the issue or decide that everything's okay and get on with the mission. Next after that is a once around abort, where you have enough energy to get mostly into orbit, but you're going to have to land immediately as you come back around. The next option is a transoceanic abort landing, where the shuttle immediately lands at one of several potential runways in Europe. I didn't run this one down, but I once heard that one of these sites regularly hosted a large air show, and they always hoped that they might have an unexpected guest from NASA to liven things up. Actually, the Transoceanic Abort Landing, or TAL, wasn't quite ready for STS-1 due to technical reasons, so it wasn't going to be on the table for this mission. But astronauts in the simulator, basically killing time, figured out a sort of crazy plan to load the landing software into one of the extra computers during the abort. So that was the plan for STS-1 if a TAL was needed. The last remaining option is where things get really hairy: the return to launch site, or RTLS abort. In an RTLS abort, the crew waits for the SRBs to separate. Then, with the main engines still running, slowly pitches over until they're firing first straight up, and then finally completely backwards, facing back towards Florida. After doing this for a while, their horizontal velocity will be cancelled out so that they can shut down the engines and ditch the external tank. But since you don't normally ditch the external tank in the atmosphere, even if it is pretty thin where this would happen, they have to be a little more dynamic. They pitch down, punch the ET SEP button, and then pitch back up, essentially throwing the ET off of them. Oh, and during all this, they're running the OMS engines non-stop to try to burn off fuel and reduce landing weight. Once the ET is gone, the plan is to glide back to Florida for a nominal landing. There were some tentative suggestions to actually perform an RTLS abort as a test, but John Young put his foot down on that. One quote I saw sums up his feelings about the maneuver. He called it 6 miracles followed by an act of God. Another quote had a technician asking Young what displays he wanted on the computer during an RTLS abort. Young said he didn't care since he'd be covering his eyes and going, "Ah!" Why did John Young have a say in this? Well, because our old friend here had moved up to the head of the astronaut office and would be commanding STS-1. I'm going to be a little tight on time on this episode, and we've gone through John Young's biography 4 times already. So I'll just say that if you'd like to know more about him, check out the episodes on Gemini 3, Gemini 10, Apollo 10, and Apollo 16. This is his 5th of 6 flights. Joining Young in the right seat, flying as pilot, was rookie astronaut Bob Crippen. Robert Crippen was born on September 11, 1937 in Beaumont, Texas. Crippen, who often went by the nickname Crip, earned a degree in aerospace engineering from the University of Texas at Austin and was the latest in a long line of astronauts who earned their wings flying with the United States Navy. After a few years of flying planes on and off of aircraft carriers, he moved on to the Air Force Research Pilot School at Edwards Air Force Base in California. Once he graduated, he stuck around for a while as an instructor, until in 1966 he got a call seeing if he'd like to fly in space. But not from who you think. Rather than the call coming from Deke Slayton over at NASA, the call came from the folks putting together the Air Force's space station, the Manned Orbiting Laboratory. Cripp trained for his spaceflight while helping to develop the military space station right up until its cancellation in 1969. Despite a significantly overstaffed astronaut corps, NASA took on a big chunk of the MOL group, at least in part to maintain goodwill with the Air Force, whose support was critical for the space shuttle. Cripp, along with the rest of his group, were explicitly told that there were no flights coming for a long time, but he wanted to fly in space, so he took his spot on the bench. In 1972, he commanded a full-duration Earthbound simulation of Skylab, which provided crucial feedback that allowed the real Skylab to succeed. As work on the space shuttle ramped up, he applied his interest in the computers and software that were so central to the next-generation spacecraft. He figures this was at least part of how he got the coveted seat next to John Young for this mission. This was his first of 4 flights. After a hiatus of nearly 6 years, countless engine tests, endless hours of training, and an unspeakable number of thermal tiles to deal with, April 10th, 1981 dawned and it was time to fly. Well, almost. One of the computers failed to sync up with the rest, so the launch had to be scrubbed. In a stroke of luck, computer engineers took only 1 day to determine that the sync failure was both rare and benign, so they would be able to try again with no modifications. The scrub also gave technicians a chance to reset a particular switch in the back of the cockpit. This switch would flip the telemetry system from primary to backup, but no one imagined that the commander and pilot would need to activate it during ascent, so it was impossible to reach. Well, someone decided that they better have access to it after all, so they had to come up with a way for the crew to operate it. The solution was that someone tied a string to the switch and gave the string to Bob Crippen, telling him to only pull it if necessary since he couldn't unpull it. During the hour spent on the pad before the April 10th scrub, Crippen fell asleep. His arm dropped and he pulled the switch. Suddenly, mission controllers had to decide if they could live with the switch being in the wrong position. So the unrelated scrub was probably for the best. I love stuff like this. Multi-billion-dollar spacecraft, thousands of experts in the loop, and Cripp accidentally pulls a switch on a string. The scrub was also fortuitous, if only for symbolic reasons, since it placed the second launch attempt on April 12, 1981, exactly 20 years after Yuri Gagarin was fired into orbit. We sure did come a long way in 20 years. At 7 a.m. local time, the correct sequence of valves were opened, the 12 turbo pumps whirred up to ludicrous speed, and all 3 space shuttle main engines roared to life. For a few moments, their asymmetrical thrust tilted the entire stack forward about 2.5 feet in a movement delightfully known as the twang. When the shuttle rotated back to vertical, a second set of commands were issued. The SRBs, never before used on a human spaceflight, were ignited and let loose a torrent of flame. The frangible bolts holding the entire stack to the mobile launch platform were detonated, and Columbia's first flight was underway. Unbeknownst to the crew, all was not quite well. Despite the best efforts of the sound suppression water deluge system, the force of the SRB's igniting had generated a shockwave, which bounced off the pad and slammed into the aft section of the orbiter. The body flap, which is a control surface located below the engines and is critical for re-entry, was forced out of position by 5 degrees. Additionally, a strut in the forward RCS module buckled, narrowly avoiding an attitude fuel system rupture and immediate abort. But nobody would realize it until after landing. Columbia cleared the tower already moving at over 100 miles per hour. Soon it was time to throttle down the main engines to reduce stresses on the vehicle during the period of maximum dynamic pressure. Max Q passed, the call came over the radio, "Columbia, Houston, you're go at throttle up," and the engines throttled back up. By this point, the out-of-position body flap caused the shuttle to pitch higher than expected, lofting the trajectory, but the computers adapted and Columbia continued on. Around 2 minutes after liftoff, the call came that the crew was negative seats. They were too high and moving too fast to use their ejection seats. So for the rest of the ascent, their only way home would be the shuttle. Next up was SRB SEP. The 2 massive solid rocket boosters burned out, and 2 minutes and 11.7 seconds after liftoff, the proper explosive bolts fired, 8 small separation motors ignited, and the SRBs were dropped off the side of the structure. The astronauts were treated to the surprise sight of a blast of flame covering the windshield as the separation motors did their work. With the raucous solid rocket boosters gone, the ride smoothed out considerably. All that was left was the long, slow climb to orbital velocity, powered by the 3 comparatively tame SSMEs. Columbia was already above most of the atmosphere, so there was little to get in the way. At 5 minutes and 15 seconds, Columbia was traveling at 7,500 miles per hour. Just 45 seconds later, it had already put on an additional 1,300 miles per hour. After 8 minutes and 34 seconds, the SSMEs fell silent. Columbia was flying just shy of orbital velocity. With another set of computer commands and a little work from the RCS thrusters, the external tank was jettisoned and Columbia scooted up, moving away from the inert tank. The tank was on a path to re-enter and break up over the Indian Ocean, and at the moment so was Columbia. With 2 last little pushes of the comparatively small OHMS engines, one lasting 86 seconds and one lasting 74, Columbia was placed into its final orbit. 246 kilometer perigee, 274 kilometer apogee, and 40.3 degrees inclination. And for a second time, John Young ushered a spacecraft into orbit on its first piloted ride. If there was any doubt that Columbia and its crew were now in orbit, it was soon diminished when an unintentional tradition was continued. The crew noted a few washers and screws floating around the cabin. Every time. John Young and Bob Crippen became the first to experience events that NASA's army of engineers, technicians, and astronauts had only dreamt about for so many years. The fiery departure of the SRBs had been an alarming surprise. A less alarming but more unwelcome surprise was the volume of the RCS thrusters. They may be small compared to the overall vehicle, but the thrusters packed a punch. Young compared the front thrusters, just a few feet removed from the crew cabin, to a howitzer artillery gun. And before you could say, how come there's sound in space, the sound was transmitted through the structure of the orbiter. When I was commenting on the surprising volume of the RCS thrusters, a friend from work who had been part of the shuttle attitude team told me a fun fact. So here's a second-hand fun fact. For later missions, there was a flight rule that during sleep periods, attitude control would only be performed with the RCS thrusters in the back, since the ones in the front were so loud. It's the little details that makes a mission go smoothly. But the crew was about to discover a less fun fact. When Crippen opened the payload bay doors and looked towards the aft of the spacecraft, he immediately noticed that something was wrong. on the forward part of the two OMS pods, several tiles were missing. This section of the shuttle was not subject to the harshest conditions during re-entry, and thus were covered in the low-temperature tiles, but it was still a cause for concern. If superheated plasma were to burn through the gaps in the thermal protection system, it could cause the OMS pod structure to fail, or even detonate the hypergolic fuel inside. Even if these were relatively low-risk tiles to lose, however, it raised the question, what if these weren't the only missing tiles? STS-1 did not carry the robotic arm, and even if it did, it wouldn't be long enough to inspect the orbiter's underbelly. I have to wonder, as Young and Crippen took a close look at the missing OMS tiles, did they think of the tile repair kit that they had left back home? As problems emerged during the development of the tile system, there had been a push to fly with a tile repair kit, but even the concept itself was controversial. Part of the objection was, if we think we need this, we shouldn't even be flying. But it was also controversial because in testing, it wasn't obvious that it wouldn't just cause more damage than it fixed. Down on the orbiter's underside, there was nothing to grab onto, nothing to hold an astronaut in place as they repaired tiles. The only option would be to stick a structure onto the good tiles, which was likely to make a bad problem worse. Once again, John Young put his foot down, and the tile repair kit did not fly. Analysis teams on the ground feverishly got to work trying to determine the impact of the tiles they knew were missing, as well as the likelihood and impact of other missing tiles. Meanwhile, the crew tried to put the tile issue to the back of their mind and carry on with their mission. In a sense, that mission was pretty simple. Basically just check that everything was working as expected. None of the tasks were particularly tricky, but there were a lot of brand new systems to look at, and only 2 guys to do the looking. One of whom had never been to space, so was concerned about being affected by the dreaded space adaptation syndrome. Spending your first 2 days in space doing nothing but puking would be a bummer. So when Columbia first arrived on orbit, Cripp moved as slowly as possible, making sure to stay oriented as if the cabin were still on the ground. It was a good idea to be cautious, but it turned out that Cripp was one of the lucky ones who were completely unaffected by the disorienting effects of zero gravity. One system that gave the crew trouble was the Development Flight Instrumentation Recorder. The DFI recorder was the only payload for this flight and was essentially just a fancier version of an airplane black box. With so much unknown about how the orbiter would perform, especially during entry, this was an important instrument. So ground controllers were dismayed to learn that the crew were unable to turn it off as planned. Something in the system was busted and it wouldn't stop recording. In order to prevent it from using the entire tape, Cripp pulled the circuit breaker. Throughout the flight, he would have to manually reinsert the circuit breaker, allowing it to record more data. This posed a problem for re-entry since the circuit breaker was inaccessible from the front seats of the flight deck, and there was no string that was going to help this time. The eventual solution was to just turn it on right before strapping in and hope for the best. It turns out that all the effort was for naught, though. Once safely on the ground, the recorder was extracted, and it turns out that a loose piece of debris had jammed the entire unit. It only recorded the first 31 minutes of the flight. Whoops. After an eventful first day on orbit, it was time for the crew's sleep period. Crippen slept strapped into his seat, while Young apparently opted to just drift around the back of the flight deck. Neither slept well, however. They obviously had a lot on their minds, but on top of that, the temperature controls in the crew cabin were acting up, and the astronauts found it too cold to sleep, though that would be fixed by the next night. While the crew slept, Mission Control continued to work the tile problem. After running the numbers, they determined that Columbia should be able to handle the missing tiles that the crew had spotted, but there was still concern that there might be more extensive damage out of sight. Little did most of Mission Control know that they weren't the only space-focused group working on the problem. Out in Sunnyvale, California, the Air Force was working on a plan to photograph the shuttle using, assets? The press conferences at the time made plenty of references to ground-based assets, like telescopes, but these assets were not that. The Air Force, along with a select few at NASA, worked the numbers to perform satellite-to-satellite, or SAT-squared, imaging, using one of several cutting-edge KH-11 Kennen spy satellites. In fact, the plan had always been to leave this sort of imaging open as a possibility. Eagle-eyed insiders could have, but as far as I know, didn't, noticed that the final orbit numbers were slightly different than originally planned. This set Columbia up to be on a path where such imaging was even possible. Eventually, the astronauts were instructed to hold the shuttle at a specific attitude for a while and not ask too many questions. Crippen, who held impressive clearance as part of his work with the MOL, knew what was up, but Young could only guess. Though I bet he had a pretty good guess, especially when something twinkled by the cockpit windows over 100 miles away. After a few such attempts, with satellites passing as close as 67 miles, word started to get around Mission Control that they were out of the woods, though nobody was really sure why. Some people saw photos that couldn't be explained with any known technology, while others just had to hear the happy news. Nobody was completely sure how, but they knew that Columbia's heat shield was okay. If this meeting of the civilian and military space worlds sounds like it could be interesting, you're right. Basically everything I just mentioned about this sneaky imaging I learned from a book called Into the Black by Roland White, which I can't recommend enough. Seriously, it's fantastic. Go check it out. But with Columbia's integrity confirmed, the only place left to go was into the orange and pink glow of re-entry. Re-entry on the shuttle is a little different than we're used to. So far, we've had the purely ballistic Project Mercury, and then Gemini and Apollo, which use the modest lift generated by the capsule to nudge its entry trajectory side to side. With the shuttle, rather than a relatively quick and punishing trip through the upper atmosphere, we'll sort of be hanging out there for a while. The extended re-entry was possible thanks to the big delta wing and helped to keep re-entry forces pretty mild, only around 2 Gs. The trade-off was that it made the approach more complicated and the vehicle would have to spend longer resisting the heat. Re-entry starts off pretty similar. Around 62 miles, or 100 kilometers, a gentle pink glow begins to form outside the windows. You can't even see it unless you re-enter during local nighttime. The pink soon transitions to orange, which is often compared to being inside a neon tube, but it's a softer glow. With no burning bits of ablative heat shield shedding off, it's not like the fiery inferno of Apollo. And the differences don't end there. Since the shuttle needed to land at a specific point, but didn't have engines to try for a second landing, energy management was the name of the game. Initially, the shuttle would have too much energy, which would result in overshooting the landing site. To bleed off speed, the shuttle would do a series of banked turns. And when I say banked, I mean it. It took me a while to grasp just how crazy the shuttle attitude looks during re-entry. Picture the space shuttle orbiter in your head. If you've got a toy or model, it would help. Start with the belly down and then pitch the nose up 40 degrees. Already this surprises the people who imagine the shuttle flying nose first like an airplane. Remember, we want to present a blunt face so that we can generate a shockwave and keep that shockwave a few inches away from the vehicle. Now, to see just how crazy the rolls are, maintain that 40-degree pitch, but roll the orbiter 70 degrees to the side. The result is a shuttle that almost looks like it's flying sideways, not even pretending to look where it's going. Maybe it's just me, but this looks so strange that I have a hard time believing it really worked. But when you follow the numbers, that's where you end up. Oh, and while it's flying at this ridiculous attitude, it's traveling at 24 times the speed of sound, around 50 miles up. Yikes. As I mentioned earlier, re-entry was probably the most uncertain part of the entire mission. The crew knew roughly what to expect, but also had to use their judgment to tell between what was normal, if unpredicted, behavior, and what was an actual problem. I imagine it would be easy to overreact to a perceived problem and cause a real problem. Well, during the first bank, they got their first moment like this. As the roll proceeded, Columbia also began to yaw to the side by 4 degrees. The fact that the meter measuring yaw only went up to about half of that should tell you about the expected yaw slip. After about 40 seconds, the autopilot eventually figured out how to damp the unexpected yaw, but it must have been a tense 40 seconds, and it would certainly result in updated autopilot tuning later. Another major deviation came from the body flap mentioned earlier. It helped to shape the hypersonic flow passing across Columbia's belly and was expected to top out at around 7 degrees of extension. Instead, it ended up at 16 degrees, exposing it to harsher conditions than predicted. So it's a good thing it was in working order. If the SRB shockwave slamming the body flap at launch didn't make the hair on the back of your neck stand up then, it should now. But soon the hypersonic banks were complete, the eerie glow surrounding the vehicle was gone, radio contact was re-established, and Columbia was just a regular glider, albeit one that was a little quicker than usual. The shuttle and its crew flew over California and arrived in the familiar airspace over Edwards Air Force Base. Soon after arrival, astronauts flying T-38 jets completed a carefully choreographed maneuver to arrive alongside NASA's newest spacecraft. The escort crew were able to photograph the orbiter so that any damage caused by the landing itself could be differentiated from damage sustained during the mission. They also helped call out conditions as Young took manual control, executed one long bank, and lined up for the final landing. All the years of speculation, planning, worry, and optimism came to a definitive conclusion when after 2 days, 6 hours, 20 minutes, and 53 seconds, Columbia set down in the dust at Edwards with a gentle 1.5 foot per second descent rate. After rolling for almost 2 miles, the shuttle came to a stop and the mission was over. John Young declared, "That's the world's greatest flying machine." And I'm inclined to agree. Alright, that's 1 down, 134 to go. Next time, John Young and Bob Crippen hand over the keys to NASA's new ride, sort of literally, to Joe Engle and Dick Truly. STS-1 proved that Columbia could fly, but it would be up to STS-2 to do it again and prove that the shuttle was truly reusable. Ad Astra, catch you on the next pass.